This is a production of Cornell University.
Today I wanted to go over a few of the mechanics of the class. Has everybody been able to look at the first problem set so far on Blackboard? You've all gotten it? Any problems there? Okay. With the problem set you got some websites that you can go to get a little bit more background information. Also, we now have permission from Wiley to give you the chapters of the book that's being printed. Today on Blackboard I'll post this information. The important thing is that you know that there's a password that you have to enter, and the password is Cornell. So you go to that link, you'll click to download the file, the PDF, but then when you try to open the PDF it will ask you for a password, and you type that in and you should get it. So I did it. It seemed to work okay. Again, if you have problems, please contact the TAs about that process. Okay, last time we were talking about where Moore's law might run into problems as you scale devices and make them smaller. So we're talking about getting down to a gate dimension on the order of 10 nanometers and whether you can actually keep going. This is what we're trying to scale, make it smaller and smaller. Device, when the channel length gets to be smaller, you get a faster device. So that's good news, right? It also means that if you can keep those operating voltages, that is the voltage that you apply between the source and the drain, right? If that voltage can be kept get smaller and smaller, then actually you're going to get a savings in power as well. So that's a benefit. Now what we're going to go through today is we'll talk about some of the aspects of power. We'll also talk about some of the challenges in scaling. All right, so one of the things that happens in scaling is that even though your device is getting smaller and smaller, turns out that the length of the metal interconnects, the wiring that is used to connect all the transistors together, is not really changing. Right? You still have to go to the outside world, and you still have to connect all these devices together. So the total length of the interconnects is not getting much smaller, even though you're making the devices smaller. That causes problems then, okay, because it means that there's some time delay associated with the current moving through the metal interconnects, and we'll discuss that. Also, as we mentioned that we're scaling the gate oxide. We're making the gate oxide thinner and thinner, and as you do that, the oxide gets so thin that new physics starts to take place, and you begin to get leakage through the gate oxide. You get that leakage current. And that current costs you power, so that's a problem. So let's go to the Blackboard and we'll talk about some of these challenges of scaling. You remember last time we defined the transit time, tau, that it takes for the electron to move through the channel, and we found that tau was equal to L squared over V, and that then if we scaled everything, if we said that we defined L prime as a smaller L and a V as a smaller, V prime as a smaller voltage, then we found that T prime was going to be something like L squared V over Vn. So that meant that this is with the transit time now. If we scale the device, make it, if n is equal to 2, it's twice as small, then the transit time is going to get shorter, so the device speeds up. So that's good. Now let's consider the power though. Okay, so the power is equal to the current times the voltage, right? And now we have to figure out how to get some handle on the current in the device. The current that we're talking about is the current in the channel. So we could define that as the Q, which is the charge, divided by the transit time.
What is I?
That's the current. So this is the current in the device. Sorry. So Q is going to be the charge that we generate when we apply the voltage on the gate, right? So you know that when we put a voltage on the gate, that pulls up, if it's a p-type device, we pull electrons up below the gate oxide, and we have charge, and that's the charge that's going to flow through the device. So now we have to review a little bit of your basic physics. Hopefully you remember that the charge in a capacitor, Q, is given by the capacitance times the voltage. Is that an unfamiliar to people? Who's not seen that before? Okay, a few of you. Okay, that's okay. So it's not a complicated equation. All it's saying is that if I have a capacitor, which essentially the gate is, right? I have a metal electrode separated by an insulator, and then there's electrons below it. So that's a capacitor. It's storing charge. The charge that is created on the capacitor is equal to C times V, where this is the capacitance. All right. Now, this is where we have to get a little bit more detailed about the capacitance, and so there I'll have to put up an equation that perhaps you haven't seen before. But the capacitance of a parallel plate capacitor is given by epsilon A over D, where D is in this case, the thickness of the gate oxide. All right. A is the area of the gate. All right, so that's the area of the gate electrode. And then this quantity, epsilon, is called the dielectric constant. All right? So this is a simple equation for the capacitance, and we have to get into this detail in order to understand the scaling. So that's where we're going to go with this. All right, so let's move that all the way up there. Okay, so now let's call the area of the gate, we'll approximate that as L squared, because if the channel is around length L, it's probable that the gate is about a width of L. So we'll say that A is equal to L squared. And so we can write the charge on the gate to be this: epsilon L squared V over D. All right. So that's the charge that's going to be induced on the gate. And then we can figure out that the current that's going to flow through the channel is going to be epsilon L squared V over D. That's the charge. And then we're going to divide that by tau, right? So tau is, in this case, is what? V over L squared. V over L squared over V. All right. And that's then going to become epsilon V squared over D. All right. So that's the current. So the power, hopefully I can get that up a little here. Power is equal to V cubed over D. Okay. So now we'll do the same thing. We'll play this game with the scaling, and we'll figure out that if we take V prime is going to be equal to V over N, and same thing, D prime equals D over N. Then we can see what happens to the power when we scale it. So the scaled power, we're going to take V over N here. So this is going to be V over N cubed, right? And this is going to be D over N. And so hopefully if you can move this up a little bit, that's going to give you V cubed over D times 1 over N squared. Hopefully I did that right. I think so. Yeah. All right. So what happens to the power in the device as long as I scale the voltage and the gate oxide thickness? Does it go up or down? It goes down. It goes down by a factor squared of the scaling. All right. So that's the power in the individual MOSFET. But what happens to what's really important to us is not so much the power in the individual device as the power per unit area. Is there a question?
Yeah, where did the epsilon go?
Oh, sorry. Thank you. So I missed the epsilon here. Great. Someone's paying attention. Good. Okay. So the important parameter is not so much the power per device as the power per unit area, because that's going to tell us how much our silicon is heating up. So if I want to figure out what's called the power density, or the power per unit area, I have to actually divide this by L squared. Okay, so the power per unit area, which I'll do, if we all have that, I hope. So the power per unit area then is going to be epsilon V cubed over D divided by the area, which is L squared, right? And so that is going to then mean that we're going to, if we scale, remember L is, if we scale L now, just like we scaled everything before, we'll find that the power per unit area under scaling actually is constant. Okay? What that means is that, because I'll replace this with V over N and D over N and L over N. You do all those things, it turns out you see that these are the same. There's going to be a divided by N, multiplied by an N squared, divided by an N cubed. There's going to be another factor of N. So it turns out that if you shrink everything down, the power per unit area actually doesn't change. So you don't gain anything in terms of the amount of heat that you reduce going into the whole fabricated collection of transistors. Right? The heat that's going into that is going to be constant no matter how small you make the devices. So that's actually not that desirable, right? You'd like to be able to reduce the power that's going into these things so you can use less power from your batteries or whatever it is. So the question is, how do we actually get smaller power? All right. Well, one thing you could say is, why don't we actually keep D so we could get less power dissipation if D were constant, right? So if I didn't scale D, right, then what will happen is that the power density would look something like this, right? Okay, would there be a factor of N there? So if I don't scale D, but I scale everything else, then actually I can get lower and lower power densities, which would be good. So the question is, why do we have to reduce D as we scale the whole device down? What's important about the gate oxide thickness? Yeah, did you have?
Well, I was going to, the thickness of the gate oxide prevents leakage, so wouldn't you want to keep D normal?
Okay, that's a good point. What he's saying is that if we get D thin, it's going to leak. That's actually, so we're going in the wrong direction, right?
Did you forget epsilon again?
Ah! I knew why I wrote the proportional sign here, so let's just do that. Okay, there we go. All right. Yeah, you're right. There should be an epsilon in there. Any other ideas about why D we want to make it smaller?
Because the electric field wears off as you get farther away, so keep that significance.
So what you're saying is that if you made D really thick, then you wouldn't have much field at the bottom where the electrons are supposed to be. Okay, that's actually getting close to what we really need to think about. The point is that the thickness of the gate oxide affects the current, remember? So if we go back down here, see if I think on the other board I have it. Okay, so it's right here. If I make D bigger and bigger, relatively speaking, what happens to the current in the device? Smaller, okay? Now, can we actually have a device where we get less and less current flowing through it? The answer is ultimately no, because if you go to zero current, you have no signal. Right? You have no, remember that the current that's flowing through there is transmitting all your bits through your processor, and it's important to keep that signal level high. So if the current gets too small, we don't have enough of what's called gain. All right? So it's important that we have gain in our device. All right? And the gain will ensure that our signals are transmitted through the device, through all the different transistors at levels where you don't get errors, right? So you need high current gives us good gain, right? Which means no errors. All right? But if I'm trying to send a bit through and the current is very low, then there may be the computer may make an error, right? And so the point is that we need to have enough current in these devices. And so the trend in the industry has always been for D to be approximately L over 45. So whatever the width, the channel width is, the gate oxide thickness has always been about a 45th of that. And so that scaling rule has been followed over the last roughly 30 years as devices have gotten smaller and smaller. Now, the point is that if you get to 45, if you have 45 nanometer technology, so if the gate width is 45 nanometers, D is about 1 nanometer. All right, it's very thin. This is about 10 atoms. Okay, so this is exactly the problem that was mentioned earlier in the question, is that now when the gate oxide thickness is very small, we get leakage through the device. That leakage is going to actually cost us power because it happens regardless of whether the device is on or off, right? You're going to have some voltage on the gate and the current's going to flow, and whether or not your channel actually has current in it. So it costs you power. So let's talk a little bit now about where that leakage comes from, because it's a concept that's important for a variety of topics that we'll talk about in this course. So what I wanted to turn to now is discussing what's called tunneling. All right. So the origin of the leakage in these devices, when the oxide gets very small, is due to tunneling. And tunneling is a quantum mechanical effect. It's not something that you would predict from just your normal concept of how electrons behave in a circuit. You have to understand a little bit of quantum mechanics. And we're going to go into that in more detail later in the class, but I wanted to sketch out the picture for you so you can understand how it relates to the gate oxide. So what we can do is we can draw a band diagram of the junction between the metal, this would be the gate electrode here, all right, and then over here, if we have, let's say we have p-type material, so we're going to have remember we tracked electrons to the interface, so there's going to be some electrons here in the conduction band of the silicon, and here's the valence band, okay? So this should all look familiar to you, right? What I'm showing is the spatial diagram of the electron energy across this, the oxide. And so the oxide now has a width d here, all right? Okay, so this is the picture. We have electrons over here in the conduction band. Now, those electrons actually would like to get over here to this side, right? Because when we put a positive voltage on this side, right, they would like to get over there. Typically, the oxide is so thick they can't get through. But when the oxide gets to be on the order of, even on the order of 5 nanometers, then an electron current can flow through the oxide, all right? And that's called a tunneling current. Now, that has nothing to do with electrons actually getting over this barrier. All right? This barrier is about 3 volts. This would be what you would think of if it drew a picture here. This would be the conduction band of the oxide. All right? So if I were an electron and I got to that energy, I could actually travel through the oxide as a free electron. Remember, we've talked about semiconductors and insulators. If I could get up there, then I would be free. I could pass through there, and I would respond to the positive voltage. But the point is that 3 volts is a very big voltage, right? And we know that in the PN junction, when I run it in forward bias, right, in order to get over that gap, right, remember the threshold for the electrons to get over, that gap's on the order of a volt, right? So a volt is maybe something that a few electrons get over, but 3 volts is way too high, all right? Sorry. So that is not enough, that's too much energy for electrons to get over thermally. So there's no thermally generated currents. All the currents are tunnel currents. Now, it turns out that the tunnel current has a very interesting dependence on the gap, the width of the oxide. Tunnel current is proportional to the exponent of some constant, this is just a constant, K, times the thickness. That means that the current that flows through here is it's exponentially dependent upon the thickness of the oxide. So when the oxide is a moderate width, no current flows. But as you get thinner and thinner, the current actually goes up exponentially. And so that's why this problem is even worse than you'd imagine, because a change from 2 nanometers to 1 nanometer thickness actually causes a big change in current of this tunnel current. All right? So what we want to do is we want to actually keep D from getting to be too small. And that was pointed out in the question earlier, right? Yeah, it should be. Yeah, it's 3 electron volts. Thanks. So for the current to be prevented, we need to keep D large, but we can't make D too large, or else we lose the amount of charge that we can induce at the interface, because we need those electrons in the channel. So we have this problem then. We would like to keep the current large, but to keep the tunneling low. So what's the solution to that problem? Okay, it was mentioned in the video that you saw, right? Change the material. What do you change it to? High K. So did they say what the high K was? Hafnium oxide. What does high K mean anyway? Okay, sorry. Oh, so you guys, okay, so you know it's high K. What is K? K is the dielectric constant that I have written as epsilon, okay? So when they say high K, they mean high dielectric constant, all right? And so the reason is we write down the value for the current, right? It looks like this, all right? So if I want large current, I can either make D small, right? That'll boost the current up. Or I can make epsilon, the dielectric constant, larger. So now I can start to play some games with materials. And that's actually, I think, a good lesson, is that this technology can't advance unless you can actually implement new materials into your process. So materials are very important. It's a materials property. And it's essentially something given to us by nature. Right? So some oxides will have a higher dielectric constant than others. And so we can start off with air, right? So what's the dielectric constant of air? It's about 1, right? Okay, that's okay. 1. Vacuum, air, the same, about 1, okay? And SiO2, it's about 4, all right? If we have like NO, if we add some nitrogen into our silicon dioxide, then it's about 6. And then these other materials, which you can't see down there, so I'll write them off to the side here. The other materials that they actually use would be Al2O3, which is an oxide of aluminum, hafnium oxide, or zirconium oxide, all right? These all have dielectric constants of 10 to 30. So what you do is you say, okay, I'll get rid of my SiO2, and I'll add a new oxide, a different oxide. And that will increase the dielectric constant. Oops, sorry about my fish there. I don't know what that's on. It's not supposed to do that. You didn't say anything. Okay. So here's my question. Why do you think it actually gets to be more complex to introduce these oxides? What's different about how they're put on as opposed to how we do the conventional SiO2? How do we do SiO2? You remember? You heat it. You do a thermal oxidation, right? So we take the silicon wafer, we put it in a furnace, we heat it, and we get this magical, very durable, and controllably thin oxide. That's an amazing process that's given to us by nature, actually, all right? It's sort of a miracle. All right. But then the only problem is silicon dioxide doesn't have a high enough dielectric constant, so we have to now introduce other oxides. The only way to do that is to deposit them. So we talked about CVD, chemical vapor deposition, as a way to deposit metals. You can do the same thing with these other oxides, or you can sputter them on, but that adds complexity and expense to your process. So it turns out it's actually very difficult to implement these different materials in the gate oxide region. So it's a change that was hard for the computer industry to introduce. They've done it now, and it's kept Moore's law going in the direction that it should. All right, so that's the gate oxide. There's also another scaling that we need to talk about, which has to do with the interconnects. So I mentioned before that the interconnects were not changing in their length. Yeah.
Why haven't they changed the material that make these interconnects? I know you said they changed from copper, from aluminum to copper, but why haven't they changed that? Because I'm sure you could make things smaller than aluminum and copper.
Well, you can't. So that's a good question. So they've changed from aluminum to copper because the conductivity of copper is better. You can't get much better than copper. Okay. So the metallic elements, there's not much around that you can improve on. Okay. So they sort of pushed the limit with the material selection for the interconnects. Maybe you might be able to do it with silver. You have to also think about expense, right? So gold would probably be better, but you're not going to make it out of gold, right?
Right, but the ceramics, things like that.
No ceramics are going to have any kind of conductivity near metal. So you have to go with a metal. All right, so let's think about the interconnects. These interconnects are the lines that carry all the data that you're trying to process in your microprocessor. So you have to think about these interconnects as carrying voltages that are turning on and off. Right? So the signals are going up and down in amplitude, and so it could be data, it could be voice, something like that. But the point is that they're changing in their amplitude, and so there's switching. Okay, so there's switching in the interconnects. And so you can talk about as a switching delay time, right? Which I'll call it tau, but I'll call it now for interconnect, all right? And again, now we have to turn to some basic physics that probably you may have heard of, it may not, but it's not that important. If I think of my switching as, if I have a capacitor here where I've got charge stored, and I say, okay, I now want to change the voltage on this, all right, and pass a current. There's a time it takes for this current to flow around this resistor, all right? So the delay time that you can think of as when I change the voltage, to do that I have to move the charge to the resistor, so that the interconnect delay time can be approximated something like RC, where this is the resistance of all the interconnects, all right? And this is the capacitance of the interconnects with other dielectrics, all right? So the picture you've got to have in your head is that there's all these metal wires, remember, that going through the microfabricated circuit, and they're being separated from one another by what? Insulators, right? Those insulators actually then act as capacitors, right? Because they're going to have wires that are separated by this gap of dielectric. That's a capacitor. So all these interconnects are like this whole network of capacitors that are charging and discharging all the time as signals go through the circuit. So in a very simplistic picture, we can think of then the delay time as this product of the resistance of the interconnects and the capacitance associated with whatever the other dielectrics and things are in the circuit. So we can draw a real simple picture of that. So this is simplifying things down, but the aim here is to try to scale. That's what happens with scaling. So we can think of then as our little block of dielectric here, all right? Okay, so this would be a dielectric. All right, and then we can have on top of it, we could have a little piece of metal wire. All right, like that. So this is my metal. And we could define that the metal could have a height of h and a width of w here, and it will have a length. We'll call it again. We'll call this length L. Can you? Oh, you probably can't. Is that how you get that? Oops. Oh, sorry. This is length L. Maybe you can't see that. All right. And then the dielectric itself can have a thickness T. All right. So that's our picture of our metal wire on top of the dielectric. And so the delay time, tau, we're going to write it as the length of the line, which is this length here, times some resistance per unit length. Okay, so that's a resistance per unit length, times the length of the line, times a capacitance per unit length. All right? So essentially what we've done is we know that the length of the line is not going to change in the scaling. We're saying the length of the line is constant no matter how small we make our features. So we're going to pull that out and make it separate from the other parameters. All right, so since the length of the line doesn't get smaller, what we're going to look at is what happens to the resistance per unit length. All right, so what happens if so what is the resistance going to be proportional to? It's going to be proportional to 1 over h times w, right? Sorry, the resistance per unit length. Okay, so we talked about this before. If you make the wire have a smaller cross-sectional area, it's harder for the current to flow through it, right? So that means the resistance per unit length, if I make these guys smaller, the resistance goes up. So that's the right proportionality, right? Smaller h and w, bigger resistance. The capacitance is going to be proportional, again, capacitance per unit length, is going to be proportional to, again, our dielectric constant, okay? And then we'll think about, okay, there's going to be some width here. So the bigger the width, the bigger the capacitance, the more charge it can store. But for thickness, the thinner this distance is, the bigger the capacitance is also, right? Okay, so this is our rule for how the capacitance per unit length changes. And so now what we're going to do is we're going to scale everything again. So we'll scale h and w and t. So we'll make them all smaller by a factor of n. And so what you'll find is that if I do that, what happens if I make h smaller and w smaller? What happens to my resistance? It goes up by a factor of what? N squared. Okay. So my resistance per unit length, let's call it r. It's going to be r prime is going to equal the r per unit length times n squared. All right. And what happens to our capacitance per unit length? Does it change? So if I make w smaller by a factor of n and t smaller by a factor of n, it stays the same, right? So the capacitance per unit length doesn't change when I scale, all right? So it stays the same. All right? So that means that my new, maybe I can write this up on the board so you can see it. My new, when I scale, when I shrink my dimensions down, the new tau prime, right, is going to be equal to the line length squared, which we had before, times the resistance per unit length originally, times the capacitance, times n squared. So what that says is that when I shrink the dimensions of my dielectric and my wire, I actually get a longer delay time by a factor of n squared. Okay? So the delay time gets longer. And in fact, that's been the trend. So even though all the dimensions have been shrinking in your devices in the last 30 years, the delay time has been going up. All right? And so that presents a real problem because you don't want to have delay times. You want to be able to move information through the circuitry faster. And so what do? Well, the first thing the semiconductor industry did was they substituted copper for aluminum. So that actually helps because you reduce the resistance, right? What else can I play with in this equation?
You reduce the length of the line?
You could try to do that, but that's actually hard to do, right? Unless you go to a three-dimensional architecture where you can kind of cram things together more efficiently. Remember, your circuitry is actually built sort of in a two-dimensional way. Even though there's these 7 layers, things are kind of going out sideways. So it's hard to reduce the length of the lines. The other thing you can do is you can play with what? Capacitance has epsilon in it, right? Okay. So what do we use for a dielectric typically? Remember the pictures of the cross sections of the circuitry? You're putting in SiO2, right? Putting in, it may not be thermal oxide, but some kind of SiO2 you're putting in there. Its dielectric constant is 4. So what can I put in? Something with lower dielectric constant, right? What's the best thing I could put in there? Air, right. Okay, so if I could make all my wires hanging out by themselves in space, that'd be great because there'd be less capacitance. You can't do that because mechanically it's not robust. But what do they do? Does anybody know what they do? You can do air gaps. You can actually make porous material. You can actually put holes in it, all right? And on average, the dielectric constant goes down. And so it's like a foam, so like a little microscopic foam. And so it's funny that the semiconductor industry on one hand wants high K for what? For the gate oxide, but it wants low K for the dielectrics that are used for the interconnects. So it's trying to go sort of to both extremes, right? And both of those are materials problems. Okay, so at this point, I'd like to now move into a discussion about how we can solve some of these problems with really revolutionary technology. Right? New kinds of circuit designs or new kinds of materials that are not just incremental improvements from the technology that the semiconductor industry has used for years and years. All right? So all that I've described to you here, it's all incremental improvement, right? We have basically the way that we make these devices, we make things smaller, we add a new material here and there, but it's nothing dramatically different. So let's now start talking about molecular electronics. Okay? So molecular electronics, by its definition, is using molecules now, sort of building devices at the molecule scale. Right? Now the driving force for that is what? Well, you would like to be able to store and do logic operations at a very high density. Okay? So you'd like to use very, very small wires. So the idea is that you have these nanowires, right? And these nanowires are put together in what's called a crossbar geometry. And those crossbars then are going to be separated by some kind of device. So between these two wires here, there's actually something that's going to behave like a diode or a transistor or something that's going to give us the switching that we're used to with the MOSFET. Right? Now, that's what this picture is supposed to show. For those of you who have actually done any electronics, this is actually the symbol for a diode. Okay? So the idea is that between these wires, somehow you put in diodes, and then you can now begin to do logic, that is, you can switch signals at a very high density. You can think of this then as being useful for memory. So you could imagine that's a little memory unit here, or for logic. Okay, so that you could put current in, put a signal in here, and out would come out some logic response. So the driving force for this is that a MOSFET is going to be larger than your nanowires. I can't make the gate oxide and all that as small as I can make a wire. Right? You can make nanowires very, very small. So that's one driving force. The other driving force is the high cost. So as we talked about before, as you make things smaller and smaller, you need these fabs that cost billions of dollars. Is it possible to find a technology where the cost of fabrication is lower and we can also get the high density of devices? So that's where molecular technology comes in. And the idea here is that the molecular switch is actually, if it's a molecule, it's smaller than any crossing of wires you could imagine. It's only, it's like a fraction of a nanometer in dimension. And it may be possible that you have lower cost for patterning and the materials, and you also may be able to use these arrays to solve this interconnect problem. We talked about the packaging issue, right? If you've got wires coming in from the outside that are macroscopic in dimension, and you've got to get those signals down to a little transistor that's only 45 nanometers across, you have this problem of how do you shrink everything down to get the current to that point. So there may be some solutions for the interconnect problem here. Now, the issue, of course, with the molecular electronics is reliability. If you're going to put a molecule in between these wires and use that as your, your switch, the question is whether or not it's going to always be functioning when you want it to be. Will it degrade because of corrosion or some other chemical reaction? So reliability is a problem. Okay, so let's talk about what's really being done today. So this is not just somebody's, some scientist's dream in the lab. Actually, corporations are pursuing the idea of molecular technology for their products. And one of these companies is Hewlett-Packard. And this is an example of the crossbar array that they made and published. They published actually the last decade, but this is a recent publication. And this bottom part here is showing the real thing. Okay, so this is actually an atomic force microscope topograph. So what you're looking at here, it's been colorized. These essentially are bumps on the surface, and those bumps are the lines that have been put onto the surface to make this crossbar array. So this is, if you think about this, this is sort of a topographic map of the metal wires. All right. Now, up in the inset is an artist's conception of what's going on. It's showing you that between these wires is an individual molecule. And that, in fact, is the case. They've been able to put molecules at these crossing points. And so this is a real technology that's being pursued by major corporations. And so I wanted to talk a little bit about how you would make these before we go on to how they function. So I think you've seen this slide before in the first day, but I wanted to review what's involved. We've talked about how photolithography is what we use to make conventional circuits. Unfortunately, photolithography uses light. And light has a given wavelength by nature, and so the size of the features you can make is limited by that wavelength. So the driving force has always been to go to ultraviolet light because it has the shortest wavelength, so you can make the smallest features. So that's, in conventional photolithography, we now are using extremely short wavelength ultraviolet light. Now, you can even push things further by playing some tricks to make the light interfere with itself to shrink the features even further, right? So there's some very clever optics you can do in photolithography, but that's very expensive. You can also try to go further than the wavelength of the light by using electron beams to write patterns. But that's very slow because the electron beam is a thing that moves along here serially. It's like kind of like you think about my laser pointer just would have to map out sort of all my patterns, right? And it can be very slow, whereas light comes all at once. So that's really a slow and expensive process. So the alternative is stamping. In stamping, we have a pre-existing pattern, and then we actually apply some material to it, or we press it into some material, and we can transfer a pattern onto the surface. So we don't need to do any kind of beam or light exposure. So this is called nanoscale imprint lithography. And the idea here is that you've got a substrate, and then there's some layer underneath it that's a kind of a protective layer. And then you have what they call the image resist, which essentially it's like a photoresist, but now you're not. It's a plastic that kind of can move. It's viscous. You can push into it, and it can accept an imprint. And then I have my mold. Now the mold has to be something you've made already. Okay, so it's going to cost you some money to make the mold because it's going to have very small features. But once you make the mold, you can use it over and over again. And the idea is then that we put the mold into this resist layer, so it's a plastic material that can deform. We push into it, and then we pull it off, and we now have transferred the pattern in the mold to the resist. At that point, then you see you have a little bit of resist left down in here, and you want to get rid of that. So you use some kind of etching technique. So you understand how this works, right? We've talked about this before. You use some kind of etching technique to remove that residual little bit. So you etch it down. You expose the underlayer, and then what I do is I etch away the underlayer. All right. So I'll use some kind of etching technique to remove this red region from beneath here. Okay. So it could be chemical. It could be wet or dry. And so now I have empty space here. Now I deposit metal. So I put metal on top, and the metal's coming down here, and it's putting metal here. So from this picture, which kind of metal deposition do you think that I would use? We talked about evaporation, sputtering, CFD. Which one is the most directional? Do you remember? Evaporation is the most directional. Remember, that's the one that's coming off the furnace, and the atoms aren't bouncing around off of any other ones, right? So they come straight out through the aperture. So they're going to be coming straight into the material here, and so they plow right through this empty space and deposit here. They don't actually coat the sidewalls very much, right? Which is actually, in this case, is good. So in this case, you don't want the sidewalls coated. You want to have the metal right at the bottom and nowhere else. Then I dissolve away the underlayer here, and I'm left behind the metal lines. So you can imagine that this is the crossbar that I'm going to make. Now, we then have to add our molecule. All right? So the molecule is perhaps the most difficult part of the whole process, because you have to find a molecule that has interesting electronic properties. So remember, we're going to try and turn this thing into a switch. All right? So the molecule is complicated, and I'm not going to go into how it functions, but this is an example of one of them. You use chemistry to get the molecule to bind to the metal preferentially. So you figure out some tricks to get the molecule to sit between the crossbars, and that's all. It's all chemistry. And so then you end up with something that looks like this. You have your lines here, right? That's one layer of the array of lines, and you make another layer, and then between them you've got the individual molecules. Now these molecules you can address. That is, I can put a voltage on this line and a voltage on this line, and I can get to this particular molecule, right? So I could pass current through this molecule, right? And the idea of this molecule is that when I pass current through it, its conductivity is going to change, all right? So I'm going to switch it. All right? So let me show you how that works in an IV diagram. You've seen these kinds of plots before, right? Remember the diode, right? The PN junction, the rectifier, whatever you want to call it. This is voltage. This is current. And if you think about, if you just draw your attention to this line here where my laser pointer is going, right? This looks a lot like the IV curve of a diode, right? Except, so in reverse bias, so when you go into what's called positive bias, right? There's current. When you go into negative bias, you don't get any current, but then what happens? We talked about breakdown, right? Well, this is not breakdown of your semiconductor material. This is actually a changing of the electrons in the molecule, right? And so what happens then is that suddenly at this particular voltage, it's not conducting hardly, it's conducting very little current, and then it turns on. So at this voltage, you can think of this voltage here of 1 volt is actually turning this molecule on and making it more conductive. So now suddenly it's changed. And how do I know it's changed? Well, I get a lot of current now up here, and then when I come back, or if I reduce the voltage, I still get a lot of current, all right? And when I go back here, I'm getting much more current than I got here, right? And then when I get here, boom, it actually changes again. So I can now switch this molecule between two different states by passing current through it in different directions. I have a switchable conductivity. And it turns out that the conductivity here is actually arising from changes in the way the electrons tunnel through the molecule. So again, this is the picture. You've got these molecules between these metal electrodes. A molecule you don't think of actually as having much conductivity, but because the gap is small, current, and you have an individual molecule, you can actually tunnel through that guy. And by playing around with the voltages, you can change how much tunneling current flows. So now we now have a device that we can switch. So the idea here now is that I can use some logic system to pick out the particular row and column that I want to address. Okay, so suppose I say I want to go to column 37 and row 12, and my computer is going to address that through some kind of logic system. It's going to put a voltage there, all right, and I can then start switching the molecule around. Now you don't have to know all the details of this switching here. So all you have to know is that I'm going to put in a data signal here. So it's something that you can imagine it's like a bit coming from some processor. And I want to do a logic operation on it. So I'm going to close this switch, And the logic operation is going to be controlled by some of these little molecular switches here. And I'm going to control those by putting voltages between this line and that line and so forth. So you don't have to know the details of this. All you have to know is that in a transient way, I turn this on, I get a signal here, I manipulate these switches so that then I can read data out. So if you think about it, these are kind of like voltage sources here. This has got a voltage here. This is my signal coming in. So this would be like my signal coming into the gate. This would be sort of like the source and drain controls here. And then I get something out. All right? So point is that for different voltage input levels, I can get different outputs. So on trial 1, I put in 0.4 volts. I get out, depending upon how I switch it, I got a negative voltage. So I reverse the signal. Here I put in minus 0.4 volts. I get a positive voltage out. Now some of them don't work so well. If I don't put in enough voltage, then I can't do the switching right, so it ends up being 0. All right? So the point of this view graph is that you are able to do logic inversion, right, which is important for overall device, for logic devices. And I don't need to actually have too much signal here in order to get more signal out. So I can put in 0.3 volts and I get minus 0.5 volts out. So I don't need amplification because the device gives me enough voltage. So remember we talked about gain for the MOSFET, right? We need a current to flow through here. Well, you're getting a similar effect here. I'm starting in with a relatively low voltage at an absolute value, and I'm getting a bigger one out. So I actually have a little bit of gain in this thing. So it's not amplifying it enormously, but it's enough to operate in a logic circuit. So I think I'll stop here, but I just want to summarize that this kind of device can store data, so you can store bits. It gives you enough voltage out, and you can get inversion. So the possibility exists for doing computation with these kinds of devices. Okay, so we'll see you next time.